Now that we've seen how reflection and refraction work, we can start talking about lenses and mirrors. There are conventions here just like we have in the rest of physics. One, for example, is that distances are measured from the optical element. Either the lens or the mirror is the optical element. For the stuff we're going to do, in almost every case, there will only be one optical element. We may combine a couple of lenses at the end, but in general, there's just going to be one. The simplest possible thing we can start with is a flat mirror, like in a bathroom. Um, you see this all over the place, and the things to figure out from this, if you look at it carefully, you can verify this. Uh, the distance from the object to the mirror and the apparent distance from the mirror to the image are the two key things. The object distance is sometimes called O, sometimes called D subscript O, sometimes called P for some reason. And the distance to the image from the mirror is called I. The book uses DO and DI, and the rule for a plane mirror is pretty simple. It's just that DO equals negative DI. In other words, if you're standing 1.5 meters in front of the mirror, DO is 1.5, and then your image appears 1.5 meters behind the mirror. The fact that this would be negative is that tells us that the image is virtual. A virtual image tells us a few different things. First, it means you can't project it, so you can't stand there with a index card on your shoulder and try and get the mirror to reflect some light on that index card and see an image of yourself. The virtual image is on the other side of the mirror from the object, and they don't actually have any light going through them. So when you look at yourself in the bathroom mirror, you appear to be behind the wall, but of course there's nothing behind there, or behind the mirror, but there's nothing back there except drywall and wood. So there's not another room with a copy of you in it, obviously. As long as we only have one optical element, we also should mention DO will always be positive. The object distance will always call that positive if there's just a single optical element. Now, there's an interesting problem you'll see in almost every physics book, and that is what's the minimum height for a mirror that you can fit your entire body in? It's much easier to answer this if you pretend your eyes are at the very top of your head. It just makes the triangles a little bit easier, but it gives you the same answer. The answer does not depend on your distance to the mirror, and the answer is half of your height. So if you imagine the eyes on top of your head looking out at the very top of the mirror, you've got that direct reflection back so you can see your eyes. If you imagine looking all the way down to your feet, you would be looking halfway down the wall, and that could be the bottom of the mirror. You don't need any of the mirror from halfway down to the floor. So you don't need a full-length mirror. You need one that's half your height. And we know this because we have the law of reflection, theta incident equals theta reflected. I was once asked an interesting question about this by a student, and that is, you imagine you have a small hand mirror and you look in it and can see the whole moon. What if someone on the moon had a gigantic telescope, and it's bigger than any that exist or probably ever will exist, but we can still talk about it? What if they had this gigantic telescope? They can look over your shoulder. Will they see the entire moon in the mirror, and therefore they would be fitting their entire body in a mirror much smaller than half their height? The way to figure this out, if you get a pair of binoculars, you can do a version of this experiment at home. And that is, look at yourself in a mirror and see how much of yourself you can see in this hand mirror when you're close to it, and then back away from it looking with the binoculars. All they're going to do is help you see what the mirror shows when it's far away, and you can see when you back across the room, can you fit more of your body in the mirror? You should give this a try if you have access to binoculars.